Have you ever stopped to think about how engineers do it? How they take something complex and three-dimensional, like a jet engine or a whole building, and somehow capture it perfectly on a flat 2D piece of paper? It sounds a little like magic, but it's actually the bedrock of all modern design. And in the next few minutes, we're going to pull back the curtain on the elegant, super powerful method they use to solve this exact problem. So here's how we're going to break it all down. First, we'll talk about the basic building block of any drawing. Then, we'll get into the two essential views that let us see in 2D. After that, we'll dive into the real fun, the double tilt challenge. We'll even walk through an example step by step, and finally, we'll see what that finished blueprint looks like.
All right, first things first. Before we can even think about translating 3D into 2D, we have to get on the same page about the most basic piece of the puzzle. Think about any object around you, maybe a computer mouse. To an engineer, that's not just a mouse. It's a collection of simple, fundamental shapes. In engineering, every single complex object, no matter how intricate, is first broken down into its basic two-dimensional components.
And it all begins with this one core concept, the plane. Now, for what we're doing, a plane is basically a perfect 2D surface. It has length, it has width, but, and this is the important part, we pretend it has absolutely zero thickness. It's kind of like the ideal flat world where all our drawings are going to live.
And these shapes, squares, circles, rectangles, they have a name: plane figures. You can think of them as the fundamental Lego bricks of engineering. Every amazing blueprint you've ever seen is just built up from these simple little pieces. Okay, so if everything is just a collection of flat shapes, how in the world do we use them to describe something that's actually 3D? Well, that brings us to the core technique, which involves using two essential views to create a sense of depth. To get how this works, just look around the room you're in right now. Think of the floor as one huge flat surface, and that wall right in front of you, that's another one. These two surfaces, the floor and the wall, they're going to be our reference points for everything. So our first reference, the floor, is what we call the horizontal plane, or HP for short. This is the surface that gives us our bird's eye view, what we see when we look straight down on something. And the second one, our wall, is called the vertical plane, or VP. This is the surface that lets us see the object head-on, from the front, as if we're looking straight ahead. Now this is where the magic really happens. We create our 2D drawings by projecting the object onto these two planes. Think of it like shining a light and casting a perfect shadow. The shadow that falls on the floor, our HP, becomes the top view, and the shadow on the wall, our VP, becomes the front view. This whole method is called orthographic projection, and here's the kicker. With just these two flat views, we can perfectly mathematically define any 3D object.
Okay, that's all well and good for an object that's just sitting nice and flat. But let's be real. When do things ever stay that simple? This brings us to what I like to call the double tilt challenge.
This is the real test, right? How on earth do you draw something that's not just tilted away from the wall, but is also tilted up from the floor at the very same time? This is where the system really shows off its power. Usually, a problem like this gives you three key pieces of the puzzle. First, the object's basic shape. Second, how its main surface is tilted relative to one of those planes. And third, how one of its edges is tilted to the other plane. These are the clues we have to work with.
So, enough theory, let's actually solve one. We're going to do a step-by-step walkthrough of a classic problem, drawing a rectangle that's tilted in two different directions.
So, here's our mission, straight up. We've got a rectangle, 30 by 50 millimeters. Its surface is tilted 45 degrees to the floor, and one of its short sides is tilted 30 degrees to the wall. Our job is to draw the top and front views.
Now, here's the absolute secret. You can't solve this all at once. If you try, you'll go nuts. The trick is to tackle it in three separate stages. First, we make it easy on ourselves. Pretend there are no tilts and just draw the object's true shape. Then, we add the first tilt, and only after that's done do we add the second tilt. We're building up the complexity one easy step at a time. So, for stage one, we just ignore the tilts completely. We imagine our rectangle is just lying perfectly flat on our floor, the horizontal plane. So if you're looking straight down, what do you see? A perfect 30 by 50 millimeter rectangle, its true shape. And what about the front view, looking from the front? Well, since it has zero thickness, all you'd see is its edge, just a single straight line, simple as that. Okay, on to stage two, the first tilt. We take that flat rectangle and we lift one edge up so its whole surface is angled at 45 degrees to the floor. Now, in our front view, that simple line pivots up to a 45-degree angle. But the really cool part is what happens to our top view. Because the rectangle is now angled away from us, it actually looks shorter from above. This optical illusion has a name. It's called foreshortening, and it's absolutely key to creating that feeling of depth.
And finally, stage 3, the second tilt. We take that entire foreshortened top view we just made, and we rotate it on the floor so its short side is sitting at a 30-degree angle to our wall, the VP. Once we've got that locked in, the very last step is just pure projection. You draw vertical lines straight up from every corner of your new top view, and where those lines cross the horizontal lines from your tilted front view, bam! That gives you the 4 corners of your final, crazy, doubly tilted shape.
And with that 3-step process in the bag, we're done. Let's take a look at what we've actually created, the final blueprint.
And there it is, the complete solution. I know, it might just look like a couple of weirdly shaped quadrilaterals on a piece of paper, but together, those 2 flat views contain every single bit of information needed to precisely define that object, tilted perfectly in 3D space.
So you might be wondering, why go through all this trouble? I mean, a pictorial sketch, like the one on the left, is great for getting a quick idea of what something looks like, but you can't build anything from it. The method we just used, orthographic projection, creates the views on the right. They might not be as pretty, but they are dead-on precise. They give a manufacturer the exact dimensions and angles they need. This isn't just drawing, it's the language of how to make things. And really, if you take away just one thing, let it be this simple but incredibly powerful idea. The absolute key to solving a complex double inclination problem is to just break it down. You solve one tilt at a time. You turn a difficult 3D puzzle into a series of much, much easier 2D steps. It's kind of wild when you think about it. From a spaceship to the smartphone in your pocket, every complex object ever designed and built by a human being started out with just a few simple views like the ones we've just made. It all began as just lines on a flat surface. So the only question left is, what will you design next?